When charges are moving, we still have the rule that charge must be conserved. That means we can say two things about currents in wires. First, the current in a single wire must be the same at all points. This seems obvious, but can be a surprising source of confusion in students who are shown light globes in series and think that the globe closest to the positive terminal gets the most current, while the other globes further down the line get less. The other effect of conservation of charge is that at any junction of wires, the total current going into the junction must equal the total current coming out. This is important for analysing circuits, so more about this later. Now to introduce something called current density. If a current is the same at all points in a wire, then if the wire becomes thinner, the current will have to become more concentrated. So we need to have a quantity called current density. It has the symbol capital J. It is a vector that moves in the direction of the flow of positive charge, and its magnitude gives the current per unit area in the wire. So it is measured in amps per square metre. You can see that the current I then is the integral of J over the cross-sectional area A of the wire. But we're just looking at uniform current density, and so J is just current I over area. Current density is important to know for circuit designers because wires have a non-zero resistance, which results in them heating up as current passes through. The current density must be kept sufficiently low that the wire doesn't melt or burn up its plastic coating. If wires must carry a large current, they have to have a large diameter. Let's work out the maximum safe current density in a 14-gauge wire. You notice that on our table there, the 14-gauge wire has a diameter of 64 mils, where 1 mil is 1/1000th of an inch. So in our calculation, I'll give you the metric equivalent. So we want the current density in a gauge 14 wire, and that has a diameter of 0.0016 metres. We're also told that we can have 15 amps of current flowing through it. So we need the cross-sectional area because our current density is just current over area. Cross-sectional area, pi r squared, and r is 0.0008. That gives us a cross-sectional area of 2.01 by 10 to the minus 6 square metres. So current density will be 15 amps over this small cross-sectional area gives 7.5 by 10 to the 6 amps per square metre.